Okay guys, let's do this math induction problem together. So in math induction, there's two things that you have to do. First of all, you have to prove that something is true that the thing is true for n equals 1. And after that, after you prove that it's true for n equals 1, you want to prove that it's true for n equals 2, 3, 4, 5, 6, and so on. So in order to do that, you have to prove that assuming it's true for n equals k, k being any number, any integer, so assuming that it's true for n equals k, k being any integer, it's also true for n equals k plus 1. It's true for n equals k plus 1. So basically, if you can prove that it's true for n equals 1, and then you can prove that if it's true for n equals k, it's true for n equals k plus 1, then let's say n equals 1. Then that means that it's also true for n equals k plus 1. So it's also true for n equals 2. And then if it's true for n equals 2, then it's also true for n equals k plus 1. So 2 plus 1 is 3. So it's also true for n equals 3. And then basically this just keeps going on and on. So you just proved that it's true for all n. Okay, so first of all, let's do the first step here. Prove that it's true for n equals 1. So when n equals 1, we have just this term right here. So 1 times 2 to the power of 0 equals 1 plus, and we're going to insert 1 here for n. So 1 plus 1 minus 1 times 2 to the n. Or, sorry, times 2 to the 1. Okay, so 2 to the 0 is 1, so 1 times 1 is 1. 1 is equal to 1 plus 1 minus 1 is 0, 2 to the 1, anything times 0 is 0. So 1 equals 1, and we've proved that it works for n equals 1. Okay, the second step is to prove that if it's true for n equals k, k being any integer, it's also true for that integer plus 1. So basically, if we can prove both of these, then we can prove that this works for everything. Okay, so let's move on to the second step. So first we're going to assume that it's true for n equals k. So if we assume that, then that means that 1 times 2 to the 0 plus all this stuff all the way to k times 2 to the k minus 1, I'm just inserting k into n right here, is equal to 1 plus k minus 1 times 2 to the k. So this right here is assuming that it's true for n equals k. Okay, so now we have to prove that if it's true for n equals k, it's true for n equals k plus 1. So basically when n equals k plus 1, you're just adding, when n equals k plus 1, you're basically just adding another one of these terms and inserting k plus 1 in for n. So we would get this. So everything over here, 1 times 2 to the 0 plus all the way to k times 2 to the k minus 1. And then the only difference is now we're adding the k plus 1th term. So plus k plus 1 times 2 to the k plus 1 minus 1. And that is equal to, so basically over here we're just going to add the same thing we added to the left side. Because we assumed that this was true for n equals k, which is this right here. And then we're going to add k plus 1, the k plus 1th term to both sides. And the next step after that is to try to prove that when you have k plus 1 here, if you put k plus 1 in for here and k plus 1 in for here, then it's equal to all this. So first of all, let's just add the k plus 1 term to both sides. Oops. Okay, so this is equal to 1 plus k minus 1 times 2 to the k plus k plus 1 times 2 to the k plus 1 minus 1. Okay, so basically, we have to figure out some way to make this expression right here equal to 1 plus equal to k plus 1 inserted into this expression right here. Because if this expression is equal to k plus 1 inserted into this expression here, then that means that this whole thing here is equal to k plus 1 inserted into this expression, which means that we prove that it's true for n equals k plus 1 if it's true for n equals k. So if you put k plus 1 into this expression right here, you get 1 plus k plus 1 minus 1 times 2 to the power of k plus 1. So we have to figure out some way to make these two expressions, figure out a way to prove that this expression over here on top is equal to the expression on the bottom. So let's see if we can manipulate this expression here to make it equal to the expression below. Okay, so first of all, let's just see if we can simplify some things. So we have 1 plus k minus 1 times 2 to the k. I'm just rewriting this expression. Plus k plus 1 times 2 to the... Okay, so k plus 1 minus 1 is the same as just k. So times 2 to the k. Okay, so after that, in order to get this even closer to this expression here on the right, let's factor out a 2 to the power of k. So this is the same as 1 plus 2 to the power of k times k minus 1 plus k plus 1. So yeah, if you multiply this stuff out, you'll see that it's the same as this expression up here on top. Okay, we can simplify this even further. 1 plus 2 to the k times, so k minus 1 plus k plus 1 is the same as 2k. So 2 to the k times 2k. Okay, so I can also rewrite this as, so 1 plus 2 to the k times 2k is the same as 1 plus 2 to the k, 1 plus 2 to the k times 2 to the 1 times k. And we know that if you have the same base raised to a different exponent, you can add the exponents. So 2 to the k times 2 to the 1 is the same as 2 to the k plus 1. So we have 1 plus 2 to the k plus 1 times k. And, oh, this expression here is the same as, since k plus 1 minus 1 is just k, it's the same as 1 plus k times 2 to the k plus 1. So we've just proved that these two expressions, this and this, are the same. So we basically proved that if this is true for n equals k, then it's also true for n equals k plus 1. So we've done both of these steps, and we've proved that this is true for all n, assuming that n is an integer.